welcome to Chapter 19, Section 3. We're going to be talking about magnetic force now. So what we're going to do is we're going to look at how to determine the strength of a magnetic field if we know the force on a charge in a magnetic field. We're going to use the right-hand rule to determine the direction of force on a charge moving through a magnetic field. And we're going to determine the magnitude and direction of a force on a wire carrying a current in a magnetic field. So, magnetic forces. So magnetic fields by themselves cause no forces as long as the charges are stationary or unmoving. So if a charge is just sitting here all by itself, okay, without moving, there's no force. Okay. However, if a charge is moving, so we give that cue a direction, okay, and a velocity, then we get a net force. Okay, and if you think about it, this makes sense because when moving charges move, they create magnetic fields. Right, so this charge moving here ends up with a magnetic field, right, going around it, okay? And when it does that, that magnetic field is going to interact with whatever magnetic field is already present, okay? Because like poles repel, unlike poles attract, and so we're going to get some sort of force and motion because of those magnetic fields interacting. So the key here, though, is to know that the force only occurs if the charge is moving perpendicular to the field. Okay, so that, remember, perpendicular means at right angles. So it must be moving perpendicular to the field. And this is because otherwise the fields won't interact. Maybe they're parallel, and so no force is caused or something like that. So here's kind of an example. What's happening here is you've got this plate here that's creating a magnetic field, okay? And so we've got this magnetic field going on, and what happens is this charge here, okay, this is a beam of electrons, and it enters the field, and normally it would be going straight up here, but because it's moving perpendicular to the magnetic field, okay, it is caused a curve, and so it's forced to curve until it comes all the way down and hits this plate, okay? So the reason this happens is because of the magnetic field. So that's kind of a real example where you can see this. So we have equations for magnetic force. The magnetic force is equal to the charge times the velocity times the magnetic field. This is also sometimes written this way, where B is magnetic field, and you should know that by now. Magnetic field is B, and it has a unit of the Tesla, okay, and it's equal to the force divided by the charge times the velocity. And this velocity here, okay, this is the velocity of the charge, right? And don't forget the charge is Q, okay? So you guys will get a chance to practice using these equations in class. So this is our right-hand rule for identifying the direction of a force. Okay, and there's a few different versions of the right-hand rule out there, and I don't care which one you use as long as you know how to use it, but this is the one that I'm choosing to teach you. So what you do is you point your finger in the direction that the current is moving, okay? You point your other fingers at a right angle, okay, in the direction of the magnetic field. And then if you hold your thumb out, that's the direction of the force that will act on that charge. So we'll be able to look at an example of using this in class and also just here in a minute. So a charge moving in a magnetic field will actually follow a circular path. And you saw it on that example we had a minute ago. The charges kind of took a half circle path, okay? And this occurs for the component of velocity perpendicular to the magnetic field. So if we look at a magnetic field here, right, the x's mean it's going into the screen here, or the board. Okay, and we've got this positive charge over here. So if you take your index finger, and I want you to do this, point it in the direction of the velocity, take your other three fingers, okay, at a right angle to it, and point them into the screen. Okay, then you'll notice your thumb is pointing to that center of that circle, and so that's how you know that direction happens. And if you do it, say we move this positive charge up here, okay, it would be the same thing. Now its velocity is this direction, okay, so you point your index finger in this direction, point the other fingers into the screen for the magnetic field, and you'll find that the force is pointed in that direction. And no matter where you put it on the circle, you will find that to be true. However, I want you to know that this is for a positive charge. So let's look at what happens with a negative charge then. Okay. So because this is a positive charge, a negative charge, the force is going to be in the opposite direction. So if we change this and made this a negative Q instead of a positive Q, now instead of our force being this direction, we're going to end up with a force the opposite direction. Okay, so the key here is to remember that for a negative charge, the force is an opposite direction. So whatever direction your thumb is pointing in the right-hand rule, the negative will be the opposite way. This is really important. So, magnetic forces on current carrying wires, okay? So, because a current is carrying a charge, that means if a wire is in a magnetic field, then there's going to be a force acting on the wire, okay? And so what happens here is if here we've got a B field that's created by something like this, okay? And right now there's no current, but as soon as you add current, okay, that is going to move. Okay, and you can still follow the same right-hand rule of the direction that the wire will want to move. Okay, you just put your finger in the direction of the current because that's the direction of the velocity. So if the current is going this way, the wire moves this way. If the current is moving this way, the wire will move in the opposite direction. Hopefully we'll have a chance to see that demo in class. So when we're doing this, we can also calculate the strength of that force, and it uses this equation where force equals magnetic field. Okay, this is magnetic field. Okay, that's B. I is current. Okay, and this is supposed to be a lowercase l, but it looks kind of funny on this screen, okay? And that is the length of our wire, the length of the wire that's in a magnetic field, okay? So you'll get a chance to practice this equation in class. That looks kind of sloppy. Just to summarize again, it's F equals B, I for current, and then L for length of field. So anytime now that we have two parallel conducting wires, okay, so imagine we have two wires here, okay, and in them we have two currents, okay, and I'm going to have two sets. So the possibilities are these two, okay. In one we have the current going this way, and in one we have the current going this way and this way, the same directions, okay. So anytime the current flows in the same direction, the force is attractive. So these two, the current is flowing in the same direction. So the force will actually draw these wires together. Because remember, they're generating these magnetic fields, so there is going to be some interaction. If, however, the current is flowing in opposite directions, then the force is repulsive. So these two wires will want to move away from each other. So let's take a closer look at maybe why that happens. Okay. So here the magnetic fields have been drawn around them, and here we've got the current flowing in the same direction. So we're looking at these wires from the top down. So you can imagine this is the case where these are the two wires, okay? And in one we've got the current flowing out, and one the current is flowing in, okay? And we are looking at it from the top, okay? So here we've got our current flowing out, and here our current is flowing in. When that happens, if you use the right-hand rule to identify the direction of the magnetic field, you'll notice, see all these arrows come through the center, right? And they're pointing this direction. So if we think about what that means is, remember, the arrows always go from north to south, okay? Now because of this, that means that this one is generating one that is running from north to south, and this is generating one that runs from north to south. So what that means is these two fields are parallel, and they're going to repel each other because we've got a south here, right? A south here next to a south here, and a north here next to a north there. So they're going to want to move away from each other. Here we get the opposite that's true, okay? If we look inside, okay, and these two, you can see we've got the current running the same direction, okay? And if we looked at these little circles in the middle, okay, what happens, right, is this arrow is coming around this direction, right? And this arrow is coming around this direction, okay? And so it creates this uniform looking field instead of these two separate fields looking. Well, remember again, north to south, right? So this one has north here and south here, and this one has south here and north here. So you notice they're opposite. So that means these two are actually going to attract each other, and they're going to come closer together. So that brings us to the end of 19.3. We'll get a chance to practice all of this in class, and I will see you there.